Back again to lecture about linear algebra. Here we start our first abstract view, the so called abstract view of linear algebra. Now, the term abstract makes a lot of people afraid. So, some anonymous person had said, don't be afraid of abstraction, it is an easy way to talk about practical things. And I don't apparently disagree with him, because he says that look at suppose you have one car and you have one house, right? Car and house are two different objects. So, if I ask you how many houses you have, house you own, you say 1. How many cars you own, you say 1. So, this number 1 is trying to indicate the quantity of both the house and the car using the same symbol. So, that is a very, very important idea, that abstraction means there is a common unifying symbol or unifying approach to things which might appear very diverse. So, when it comes to counting, a given number can show the quantity of several things. So, I have said 20 chocolates here and 20 tennis balls outside. So, tennis balls and chocolates are different, but I can say, okay, there are 20 tennis balls here and 20 chocolates here. The number 20 is written to signify the quantity of both. And so, as a mathematician, like any other mathematicians, we love abstraction. So, what we do, abstractions is a tool to unify. Of course, when I say of chocolates and balls, it does not mean that I am chocolates and tennis balls, that does not mean that I am telling that chocolates and tennis balls are same. I am telling, as when counting is concerned, when a particular action like counting is concerned, I can use the same symbol to signify or indicate the amount of both. So, here we talk about vector spaces, where large types of different spaces which are unlikely similar to each other would appear to behave similarly. So, the same as Richard Feynman once remarked, that the same situation, same equation. So, it is a kind of thing, though it looks apparently different, there is an underlying theme which is same, and that theme is brought into a single fact, and that is what we do in vector spaces. So, that is exactly what I have written here in the notes, that mathematicians love abstraction. It is a unified way to speak about apparently different things, which however has an underlying similarity which often goes unnoticed. Of course, this is not a very good idea to read from what you have written, and that is not I never do, but sometimes you feel that it is a good idea to read it. So, a lot of things which might look quite different from each other will come under a system called vector spaces. So, a vector space V is a set along with two operations. One is called vector addition, which is this plus, and which is a scalar multiplication. Please do not think that these are operations in Rn, do not think that. This sum does not mean that you are adding two vectors in Rn. No, this sum at this moment is not exactly defined. It would depend on the type of space and on which you can define a sum which you can call the vector sum of two objects or scalar multiplication of two objects. And and along with the addition, for the scalar multiplication we would need a scalar to come, and that scalar field, the scalar comes from a field. Of course, there is the notion of a general field in algebra, but here we are not talking about that field. Here we are talking about a field of numbers which are either real number or complex numbers, because that is what we need in most of the situations. So, let us keep it at that. However, if you just say, okay, now I have this set and I have somehow have made defined certain operations, this will become a vector space. No, because here you have trying to play a game, and in that game there are various manifestations of that game, right. For example, as a kid I knew in my hostel we used to play cricket with table tennis bats in our small dormitories, and cricket is of course played in the way cricket is played. Cricket is of course played with a tennis ball. So, these are various formats, but ultimately the rules of cricket followed everywhere, whether you are playing with a tennis table tennis bat and a table tennis ball, or actual cricket bat with a deuce ball, or a cricket bat with a tennis ball. The rules of cricket is always the same. So, that is exactly we need to develop. So, there must be rules by which the game is to be played. And now, in mathematics they come under a very boring name, axioms of vector spaces. This axiom what has come from the time of the Greeks, and I guess, and so it persists. I would rather call them as a kind of a rule we make up, because we see those similarities everywhere. So, these are the similarities that we have distilled out of various kind of spaces and brought them into one framework, that at least they should behave in this way, right. So, first property is called closure property. Whichever way you define your addition or scalar multiplication, it is up to you, but whenever you have two objects, say u and v, in the vector set v, then whatever way you have defined the vector addition, the ultimate result of u plus v when you carry out the operation must also be an element of v. This is the first property that is to be satisfied. If not, then you lose the plot, then there is no much fun. So, if you add two natural numbers 2 plus 3 and then you see that it is something else, it is not a natural number, that is not fun, but it is a natural number, it is 5. So, that is why there is fun, you can do something more with it. And now, if u is in V and alpha is in F, the field which is R or C, then alpha of u must also be in V. So, both scalar multiplication and vector addition, what the final outcome should be in V. This is called the closure property, that V is the final theatre in which everything has to happen, the set V, which we will call the vector space. A property which you know happens to geometrical vectors, and you will see happening in many other situations, is this property, that it does not matter whether you do the sum u plus v or you write the sum as v plus u plus v and v plus u is the same vector. It does not bother about the way you go about adding, that you first consider vector u, then add to it vector v, or first take the vector v and add to it vector u. They would actually be the same, the answer would become the same, it does not matter, right. The answer to it would anyway be the same. So, you can try it out with geometrical vectors, just draw the parallelograms and you will immediately understand, right. Where the sides of the parallelogram, the opposite sides of the parallelogram are equal and parallel, you will immediately understand that is exactly the commutativity property of vector addition. Then there is called the associative property of both vector addition and scalar multiplication. So, what does that mean? That this is a third property. So, note down very carefully: closure, commutativity of addition, and associative property means, suppose I have three vectors u, v, w. Here I missed that word u, sorry, it should be u, v, w, does not matter. So, for now suppose I first add u plus v and get a new vector u plus v which is in V, and then add w to it and get something. Instead of that, if I first add v plus w, first take u, and but I have also added v plus w separately, and then I add those u and that v plus w which is in bracket. In both cases the result would be the same vector. These ideas have all come from geometrical vectors in 2 dimensions actually, or even 3 dimensions if you want to think, but let me tell you, it is not so easy even to think in 3 dimensions, because we are sitting inside 3 dimensions, For most people, we cannot we can think very well in 2 dimensions because the space is fully in our control. Anybody who lives in 2 dimensions cannot think so well in 2 dimensions. You should read the book Flatland by Edwin Abbott to really understand how to visualize spaces. If you read, for example, more about this about geometry, more about topology, you would read or a beautiful book called The Shape of Space by Jeffrey Weeks. You would realize that we use our 2-dimensional viewpoint can be used to study 3-dimensional stuff, things which are in 3 dimension, or a 3-dimensional viewpoint can be viewed used to think about stuffs which are in actually 4 dimensions, which we cannot see. So it's not so easy to think in 3 dimensions. That's what I. So whatever examples that you want to check it out, in the first step, if you want to look at it geometrically, it's better to look at 2 dimensions because the image would immediately make it clear. Now, if alpha, beta are 2 elements of the scalar field, the field of scalars, and first you multiply alpha, beta normally, like you multiply to complex number, the 2 real numbers, and then you take the scalar multiplication with you. I am not writing the dot every time, alpha dot, you should read it, and it sometimes can confuse with dot product. So, this means this is a scalar multiplication. This is same as alpha beta times u is same as alpha times beta u. So, first take beta and take a scalar multiplication with u and construct the new vector beta u, and then scalar multiply the new vector beta u with alpha. That is same as doing what you have did on the left side, that you first get the multiply the 2 scalars alpha beta, and then with this new scalar you multiply, take a scalar multiplication of u. Both of these would give me the same result. This is called the associative property. Here comes the next 4 and 5 are 2 important things, the additive identity and the inverse. So, there would exist a number 0, which symbolized at 0. It is not our standard 0 on the real line or the origin 0 0 in 2-dimensional space, or 0 0 0 in dot 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 up to n times in Rn. It is not that kind of geometrical thing that we are talking about. It is a symbol at this moment. So, this is where abstraction is coming. I am introducing symbols. Your 1, 2, 3, 4, 5, 6 that you use in everyday life are actually symbols. So, without knowing what you are doing, you are actually in mathematical abstractions from your very childhood. So, get this whole thing out of your mind, that mathematical abstraction is something that has to be one has to feel very afraid of, right. So, there exists 0 element of u, symbolizes it in that way. That element has a simple property that whenever you take any element v and add it with it through vector addition, then it will return you the same vector v again. So, it does not change the vector when you add it to it. That is why we say nothing has been added to the vector, and hence this element is called the 0 vector, because nothing has been added to the original vector. The fifth property, fifth law or rule that we want to think about is a kind of imitating the notion of minus in our real line, negative numbers, or we are bringing in something called negative vectors. So, you give me any v corresponding to which there must be an element w, such that whenever I add v with w, it gives me back the 0 vector. So, then w is called the additive inverse of v, and sometimes w is denoted by minus v. So, this is an important property that people need to use at several times, but this is something that you have to keep in mind, that these 2 properties, additive identity and additive inverse. So, it is both, this is 0 as the additive identity, and to every element there is an additive inverse, whose addition to the vector gives you back the 0 vector. So, these are 2 very important properties that one has to keep in mind. Another is called the distributive property. It is called a distribution of multiplication over addition, right. Let us see what it is. So, I have two vectors u and v in the vector space V, and I have a lambda scalar, could be R or C. Now, what I do is I take lambda and first I make the operation u plus v and then multiply it with scalar multiply it with lambda. So, I get the vector which is on the left side lambda times u plus v. Now, instead of doing this, let me first scalar multiply u with lambda to get a new vector lambda u, then scalar multiply v with a new vector lambda v to scalar multiply lambda with v to get a new vector lambda v. So, I take this new vectors lambda u and lambda v and add them to get the vector lambda u plus lambda v. The distributive law says that lambda of u plus v must match or must be equal to lambda u plus lambda v. This is absolutely simple, you can just draw two dimensional figures. As I talk to you and as when you want to listen to this lecture again, please have a pen and paper and draw. For those listening to mathematical lectures, can draw it. These lectures I can give without any writing anything down, but the problem is that when I write every time, I am always reminded of how to make it better, how to write it better, how to think about it better, because as per my scientific hero Richard Feynman, there is nothing to unlearn. I cannot say that, oh, I don't need to think about vector spaces, the very basic notions of vector spaces anymore. So, that is the way it is. So, now what happens if I take two scalars alpha and beta, like they could be real or complex. So, when I add alpha, I first did not give it, later on I added this, because this also happens. So, alpha plus beta, here this plus is not the vector plus, that is why I have kept it segregated, this law. It simply means this is a plus in the field, it is a field operation, because this is field means they are either from R or C. So, if this is R, this is addition of two real numbers. If this is the complex plane C, then this is the addition of two complex numbers. So, here this was vector addition in V, lambda of alpha u plus v is lambda u plus lambda v, and this was also vector addition in V. But here there is a crucial difference, and that is why this whole thing has been segregated. The lambda plus this addition is addition in the field R or C, then this is equal to lambda v plus beta v. So, this addition is in the vector space V. So, this addition and this addition should not be confused. So, this is the thing that one has to keep in mind, that this addition and this addition cannot be confused. After that, we come to what is called the multiplicative property. Maybe I should write it as the 6th law and 7th law. I should write it, this should be the 6th law and that should be the 7th law. That is how your mind works when you write down things. You keep on writing, and when you change the page, you are keeping on writing, you forgetting that you have numbered there, because you are really more concentrated on this part of the thing, that how will you represent this, what will you say. So, of course, it must be very typical to me. I am sure there are excellent teachers who really can write things in such an organized way that okay, things are fine. But for me, if it is little bit of off the track, there is no issue, because at the end we are really have to talk about things, what is happening. That is the sole goal of our to know the real thing. So, multiplicative identity. So, 1 is a element of both the real field and the complex field. In complex field, 1 means 1 plus I into 0, the imaginary part is 0, and 1 in real field is the 1 that you know. So, 1 if it is scalar multiplied with u is equal to u, which means we have not scaled it in any way. That is the meaning. So, again when f is equal to R, we say V is a real vector space, when f equal to C, we say V is a complex vector space. So, this is the way we think about it. Now, examples of a vector space, because I have said that that there are very different sets which might not look like your Rn or Cn or whatever to begin with, but they are actually vector space with some under some field f, R or C. Of course, this whole thing can be given an extremely general definition, right. A field need not be just R or C, but here we just keep it with that, because most real life issues this is what would be the case. So, like Rn, which is normal vector addition and scalar multiplication, is a real vector space, but you can yourself try and prove that this is a vector space. For me, going and writing and proving it as a vector space is an exercise in obscurity, which I do not want to do, because writing the same things. Cn, that is the n dimensional complex plane or n-fold Cartesian product of the complex plane C, under the type of, this is the addition of two complex vectors and scalar multiplication, that is a complex vector space with f is equal to C. Now, take a space of two dimensional 2 into 2 matrices. Now, you know about matrices, so you do not have to worry much. So, take the vector addition between them as matrix addition, and scalar multiplication is a scalar multiplication of matrix. So, this is a real vector space with f equal to R. Now, consider a set S where every element u is not a coordinate, but a sequence. So, sequence are basically infinite, you can say infinite coordinates if you want to say like that. So, every element in this set S is a sequence of real numbers. So, now how do I define an addition and scalar multiplication between these two? So, take any two sequence u, which is given as x1, x2, xn, and any sequence v, y1, y2, yn. I am sure that you know what is the meaning of a sequence, because that is taught in very basic calculus or maybe advanced calculus to do with. So, if anyone has issues with this terminology with sequence, especially the students who are doing the course, can always contact me through email on the site, because I would not like to spend again defining what is a sequence, that will take away time from what we are doing. So, this is the way we want to add it, that u plus v is a new sequence whose ith term is the sum of the ith term of u and ith term of or nth term of u and nth term of v, that is nth term here is xn plus vn. So, what is lambda of u? So, just scale up every element of the sequence, every member of that sequence by lambda. So, here it is a real vector space. So, I would like you to prove that it is a real vector space, but once you take up your paper and just have checked up certain things are working, at least one of them, you need not do with others. I can understand that, of course, my whole aim would be to make you enjoy mathematics and not force boredom on you, to repeat and prove various classes of spaces are, you can choose any one of them and just prove for yourself, not the Rn and Cn which you know. So, other than that, you can immediately try to figure out what are those, does all the rules of vector space follow there, because a vector space would V with addition and scalar multiplication will be called a vector space if, as we have said, if all these rules are followed. A vector space cannot be, something cannot be allowed as a vector space if these rules are not followed. So, another space which we will call which will be infinite dimensional spaces, just like the space of sequence, where there is a space of some kind of convergent sequence, that is, or some kind of absolute convergence, pth power absolute convergence, that these are sequences with all these xi's are in R, such that this series of positive numbers summation I equal to 1 to infinity mod of xi to the power p is strictly less than infinite. So, the sum is a real number. So, it is convergent. This is called absolutely convergent series. When p equal to 2, then we call the space L2, which has huge applications actually. So, these are also real vector spaces, and this space LP, for example, is an infinite dimensional space. It won't have finite dimension. Another infinite dimensional space. So, you might tell me that okay, you have not really explained what is infinite dimension really. Some idea we have what is finite dimension, because finite dimension is very intuitive, because we are sitting in a 3-dimensional space. But then what is your story, blah blah, why you are bringing in these kind of strange looking spaces and telling them okay, they are vector spaces. So, now these are all the real vector spaces, but the addition, the vector addition and scalar multiplication is done in the same way as you have done here, right. So, LP is a subset or a subspace actually of S. So, now move to this CAB. So, A and B are two fixed real numbers, is a space of all continuous real valued functions on AB. Now, so let us define f plus g in such a way that whenever f plus g is a continuous function, the sum of that two functions is a continuous function. Let us understand here f and g are actually functions. These are themselves the vectors. We are not thinking of them as function values f t and g t. You must always make a distinction between the function f, the operational machine, and its output f of t or g of t. So, f is a function where f of t and g of t are real numbers. Real valued functions means it is taking an element in this line AB, in the closed interval AB, and putting it, mapping it to some real number, those kind of functions. So, the function, the operation itself. So, we are now looking at the operation itself as an element of C and B. We are just collecting those operators, those operations. We are not bothered with their numerical values at all the points of AB. But okay, you may say, okay, then how do you define f plus g? These are abstract kind of things, and you are just taking the, how do you define the operations? What do you mean by f plus g? So, we have to attach a meaning to f plus g. So, how do I attach a meaning to a function? By telling you how do I evaluate it at any given point t in CAB, in AB. I should write here for all t element of AB. So, we can at later stage put a correction. So, what do I mean by that? So, in that case, f plus g, this function operates on t in this way, that f plus g evaluated at t is same as f of t plus g of t. So, if f t and g t are continuous functions, then by applying the definition of continuity, whether the limit definition or whatever, you can actually prove that f plus g is also a continuous function. So, how do you so this is very important. So, when you are defining, you are taking these abstract objects like these are function, you really do not know. So, it is like a machine. So, you are taking two machines and telling how if I add these two machines, if I make a new machine out of these two machines, how will, or what do I mean by this? So, you have to show us how the machine functions, and in this case we have to show how the function f plus g is evaluated. What is the way of evaluating it? This is the way of evaluating it. So, for any lambda element of R, what do I mean by scalar multiplying the function f? F, again I am telling you, f is the object in CAB, not f of t. So, you have to say what is the meaning of lambda f by showing how it operates. So, lambda f, when it operates on a number t between AB, it's same as first taking the value f t, computing the value f t and multiplying it with the lambda. Lambda is in R. So, CAB is a vector space but it is a real vector space and it is an infinite dimensional space. We will talk about that later. We will give some examples of the further lectures. Please don't understand, please understand also at the same time I want to tell you that when I write lecture, it does not mean that every lecture has to be one class. When I am separating these two, sometimes what is happening, the one length of a lecture is very large. So, in a 50 minutes real time class, 40 minutes or 42 minutes or 39 minutes or 8 minutes is a full class basically. So, that is why you have to consider this, could be it is better to consider them as classes, but because it is a online thing, we have this advantage of really give as much as lectures possible, so that one can actually cover the ideas or things that one wants to finish or wants to tell the students. That is the key idea. So, in the example above, I will ask you to find the additive identity and the additive inverse. Now, an interesting fact is that additive identity and additive is a unique thing. You cannot have more than one additive identity. So, suppose you have two additive identities 0 and 0 dash, then you can write 0 dash is 0 dash plus 0, because 0 is an additive identity. If you add it to 0 dash, it will give you this is now v plus 0 is v, right. Now, because of commutativity, you can write this as 0 plus 0 dash, which because 0 is and v 0 is now the element, say v and 0 dash is the additive identity. Now, that is v plus 0 is v. So, this means that this will give me 0. So, 0 dash is equal to 0. So, it will prove the fact that they are same. Now, we will prove, which I forgot to write here. Here is a mistake. Now, my next step I should have written, we will prove that the additive identity given any element v, the additive identity is not clearly written. So, that given any element v in the vector space v, the element v cannot have two different additive identities, that there cannot be vectors w and w dash such that v plus w is equal to 0 and v plus w dash is also equal to 0, right. So, let us see. So, which means I have to prove that w must be same as w dash. So, I should write let w and w dash be additive identity to v. So, w is equal to w plus 0 and w is equal to w plus 0. This comes from additive identity. 0 is the additive identity, which is now unique, which you know. Now, because the element w dash is also an element additive so sorry, here is a mistake, this is additive inverse. I have committed blunders, I did not see it. So, w and w dash are be the additive inverses to v. Please make a correction, it is additive inverse. So, w is equal to w plus 0, because this comes from the additive identity, because 0 is the additive identity. Now, because w dash is an additive inverse of v, I can replace 0 with v plus w dash, because an additive inverse when added to an element v, if w dash is the additive inverse, then v plus w dash will give me 0, I can replace it. Now, I can again apply that associative law to combine w plus v first and then keep w dash out. But again I can use the commutative property to write w plus v as v plus w dash. But what is w? W is also an additive inverse of v. So, v plus w will give me 0. So, 0 plus w dash is again w dash plus 0, which is same as w dash, and so w is equal to w dash. So, with this part, with this description, let us stop our discussions, because that with next part we will talk about subspaces, that are there subsets of a vector space which can also become vector space, where taking the same operations of vector addition and scalar multiplication from the original vector space, borrowing the same operations, are there subsets which can also act like a vector space. We will call them subspaces, and they play an important role, and that what we are going to discuss it. So, please friends, at the end, please make a correction, let W and W dash be additive inverse to V, and what we are showing is the uniqueness of additive inverse to every element. Given any element V in V, it cannot have more than one additive inverse. So, thank you, and I would stop here for this class.